Hello and welcome to the data analysis video tutorial for the AA Instrumental Lab. Today I'll be walking you through calculating the error in an external calibration curve as well as performing F-tests and T-tests to determine whether any interference between calcium and copper ions is present. Apologies if you hear any whining or barking in the background, as that is my roommate's dog, and here is some dog tacks. To begin this data analysis, you need to make sure you have exported your data to an Excel file and have it open on any computer so you can follow along. If you don't have the data analysis tool pack already activated, please go under File in the top left corner, then to Options down here at the bottom, Add-ins in the left column, and Manage Excel Add-ins right here. You should be able to check the box that says Analysis Tool Pack and hit OK, and you will have activated the Data Analysis Tool Pack. In your Excel file, you should have data that looks like this part of my spreadsheet. It may be a different color I copied and pasted, and that turns it green sometimes. On my screen, I've got it set up the way I like it. Here we have our blanks, the calibration curve, and our unknowns, as well as a couple columns that will hopefully have everything that we need to calculate the uncertainty, or the mu x, down here of the calibration curve at a particular point. I've also included this equation in picture format down here at the bottom. So on to our first calculations. We need to figure out the average standard deviation and LODY and LOQY of our blank. I have it set up to auto-populate over here in the statistical quantities column, as well as over here in the absorbance of our calibration curve at 0. So you figure out the average, type in equals average of these 5 points, and equals STDEV or SDEV.P. Either works to find the standard deviation. Your LODY is going to be equals the average of your blank plus 3 times the standard deviation, and your LOQY is going to equal your average plus 10 times your standard deviation. Next up in our calculations are our calculations for our calibration curve. So first we need to find the slope, which you can either get from graphing it or from typing it in, such as equals slope, and you select all of your y or absorbance values, comma, your concentration values. The same sort of process for your intercept, equals intercept, and you select your y's and then your x's. So now that you've got that, you can actually find your LODX and your LODQ. Your LODX is going to equal 3 times your blank standard deviation all over your slope, the slope of your line. And your LOQ is going to be 10 times your blank standard deviation all over your slope. So we still have a few more calculations to do with the calibration curve. So we need to know the average concentration and the average absorbance, as well as the sum of the differences between the actual and average concentrations squared. So I need you to take the average of the concentration, click and drag to make this easier, and then you will need to type in the formula of the actual minus the average squared. For those of you with normal keyboards, you can hit F4 to actually put the dollar signs that keep the cells stable in there. If you have a keyboard like mine, you have to hit Function F4 because you don't actually have separate keys. And then you can click and drag. And if you have the exact same calibration curve as I do, then you'll have the exact values I do. Then you need to add all of those up with the equals sum function, and I have mine set up to auto-populate over here in the statistical quantities, And we are almost done. All right, so for error analysis, we've only got like one more calculation really. So I've already gone ahead and figured out the unknown concentrations from the absorbances I had earlier just by subtracting the measured absorbance minus the intercept divided by the slope to figure out your x. So over here in the statistical quantities, I have put the number of points as in the calibration curve as 11, or you can hit equals count and count all of your points right there. And my unknown repetitions is 1 for this current go through. You can change that. I've set this up as having 5 technically, but you will need the average absorbance right there. So we're just going to run through this with the 1 first, and then I'll change numbers and it'll auto-populate. So to figure out SY, all you need to do is go into your data analysis. You should find regression. It's alphabetically ordered. And your input Y range is going to be your absorbances. And your input X range is going to be your concentrations of your calibration curve. Your confidence level is 95. My output range is going to be right here because that's where I like it. And it should give you this nice data range. Your SY is going to equal the standard error of your intercept. And so with that, I've already put in my formula right here, so it auto-populates with 1.5131. And if I was just doing 1 unknown repetition, that would be my final. But because I did 5, I'll change that to 5 and change that to the average absorbance. And so here is my error now, which is about half of what it was, which is really good. If you can do more repetitions, please do so. And so what this means is that this one is seeing this number is incorrect. It should be 21 plus or minus 2 ppm because you cannot apply the average error to one singular point. And you'll do that for all of them. Or if you prefer doing it with your average, this one would be 22.2 plus or minus 0.8. And those are your actual values for that. And that is how you find something with confidence. All right, so now we've done our error calculations, and for that one calibration curve, you just need to plug and chug and change the values, the absorbance, the unknown reps, everything that you need there. So now we've got to determine whether copper and calcium interfere with each other significantly, statistically anyway. So down here at the bottom, I have another interference sheet, and I've already outlined sample A, which is one sample, and sample B, which is another, and we've tested them 3 times each. So what I'm going to do is I'm going to go up here, go over to data, go back to the data analysis toolpack. And you're going to want to select an F-test, a 2-sample for variances. We're just comparing the standard deviations of these values. And so you're going to select all of sample A for one and all of sample B for the other. Your alpha is going to be 0.05 and your output range, or my output range right now, is going to be there so I can see it. So we're looking at these 2 values, the F and the F critical. Now, F is the F calc we learned about in quant, and the F critical is the F table. And so what we need to know is which one is smaller. If F calc is smaller than F critical, then the 2 samples you're looking at have equal variances or similar standard deviations. For us, 0.017 is much smaller than 0.052, which means that these are equal variances. And that will change the type of t-test that we have to use. All right, so we finished our F-test. And now we need to do a t-test to determine actual significant differences between the two samples. So we started off with our f-test telling us that we had equal variances, which means that we're going to use a t-test to mean sample for equal variances. So you're going to go back up to the data tab, over to data analysis, and scroll down near the bottom and choose equal variances. If your sample has got unequal variances, you'll use the second one of unequal variances. Hit OK. It'll bring up this page. You're going to want to select the same ones that you did before, A and B separately. Your hypothesized mean difference, that's like your null hypothesis. I put 0. It just helps me. And then the output range is going to be right here so we can still see it. And so the stats that we're going to be looking at this time are the t-test and the critical, or the t-stat and the t-critical. And what we're looking for is if t-stat or t-calc, as we learned in quant, is less than t-critical, then there is insignificant difference. If the t-critical value is smaller than the t-calc value or t-stat value, then it is significant. But because I'm pretty sure a negative value is a little smaller than a 2.77 value, we have insignificant differences in our samples, which is great because it means there's no interference between calcium and copper.